Hello everyone, this is Dilleswara Rao from Aeronautical department. So last few classes we have discussing on longitudinal dynamics of aircraft stability on the way of stability. So while defining the aircraft stability, you need to find out the mathematical representation of the aircraft. So that mathematical representation can be find out by making that mathematical equations of motion. Finding the mathematical equations of motion of an aircraft, then we can find the stability derivatives also. So in last two classes, we started discussing on introduction to the longitudinal dynamics and what are the constraints of longitudinal dynamics and what are the earth axis system, body axis system. Body axis system was used for aircraft stability purpose. So that we have discussed. So now we are discussing the derivation of equations for the longitudinal stability derivatives, like stability derivatives also we have discussed in our last class, like there will be a cm alpha, cmz, and cx alpha, cxz, and what are the different types of stability. What is its significance of stability derivatives, and why these stability derivatives are need for finding out the stability constraint of an aircraft, and how we will make this stability derivatives in relation with the aircraft motion. That also we are going to find out now. So let's get into the topic. So the longitudinal static stability means what? Whenever the aircraft motion is in linear position, so it has to be stable in the condition, and it has to get the values. Forces acting on the aircraft will be stable at all the time. Okay, so in this way, how previously we have assumed some 4 to 5 assumptions of aircraft while deriving these equations. So on that way, one more assumption also we need to assume here is that quasi-steady flow. So what is steady flow and what is quasi-steady flow, that we need to see. So you all know, I think you already been seen across these types of flows in your fluid mechanics level. So the steady flow, unsteady flow, rotational flow, rotational flow, uniform flow, non-uniform flow, and one-dimensional, two-dimensional, three-dimensional flows also we have discussed on that. So steady flow means what? The properties of fluid will be constant with respect to the space coordinates at all the time. With respect to space coordinates, the properties like density, specific gravity, viscosity, and other properties also won't be changed with respect to the space coordinates. So that type of flow is called a steady flow. So here the quasi-steady flow means what? Quasi, this type of quasi term also we learned in thermodynamic process, like quasi-static process. So like it is in the infinitesimally small time, the process need to be continue all over the period. So from the time interval will be very small. Okay, so here the quasi-steady flow means what? If you are coming to our thing, so when an airflow is flowing around the aircraft, that flow will be changes instantaneously, because from state to state the flow properties will be changes. So when due to the changes of flow, when a aircraft motion is disturbed from the equilibrium condition, so if it is an accelerated flight, like if it is in a cruise condition, the flow will be the velocity will be constant. If it is an accelerated flight, the velocity change in velocity will be with respect to the time. So it must be turned to an accelerate certain mass of air, so that this change of mass, change of acceleration of air mass is called as a apparent mass effect. Like what? So here when a aircraft is flying on air. So due to that aircraft motion, the flow also will be flows over the aircraft, like you seen already. So whenever the flow is distributing all over the aircraft, so it will be the flow will be deflected over the aircraft, and the upper velocity will be low, and the lower upper velocity of air will be high, and the lower velocity will be low. Due to that, the pressure changes also will happen. So if it is in a, because of because of air object motion, the air also will flow over that one, so that air will also have some velocity. But if it is having some acceleration, like when a change in velocity is happened with that object, what it will happen, the ongoing flow velocity also will change. So due to the change of motion on an object cause a change of velocity of an air is called as a apparent mass effect. Apparent mass effect means the amount of air flowing over that aircraft also will have a different velocity. So this assumption, like a quasi steady flow, makes a problem simpler, and like what here the steady flow means what the flow properties won't be changed with respect to space, but in reality what it happened, there will be a changes in flow velocities, flow properties due to that object motion. So that is why we are calling as the flow motion will be very less time. Infinitesimally small time the changes are been happening, but the changes are happening. So that it is termed as a quasi steady flow, not a steady flow. It's like a quasi steady flow. Okay. So the for higher Mach numbers, like we can say like subsonic Mach numbers in a higher range, like more than 0.8 and higher. So this assumption can be made lead to theoretical results, like we will not be satisfactory to predict the actual performance of aircraft. So for these cases, compatibility effects can be taken into account for the use of stability derivatives of Mach number in equation, because whenever due to this sudden changes in flow and sudden changes of aircraft velocity, with respect to that, the fluid velocity also will change, so that the stability constraints also will change. And the stability constraints we already explained with the stability derivatives only. That means here the stability derivatives will be a major constraints, like these will place a major role on finding out the stability of aircraft. So for that, so for subsonic stability derivatives, the most accurately determined while with the internal testing, like whenever if you are doing the different flow tests in internal testing only, we can know what are the maximum attainable values for this stability derivatives. So quasi steady flow will exist as a result of this assumption. The derivatives with respect to rate of change of velocities are omitted, except those with respect to the W, like the W naught here, the W naught. Sorry, it is misplaced. So the W naught means what? We already said there will be changes we are considering in stability derivatives will be U naught and W naught. So due to that, U naught will be the linear position, already that the axis notation also we already said. So in the Z direction it will be W naught, and in the X direction it will be U naught. So due to these changes only we are considering for finding out the stability derivatives. So which will be, this W naught changes will be retained to account for the effect of downwash in the horizontal stabilizer. So what is this downwash? So downwash means whenever whenever there will be a flow is flowing over the aircraft, like you see when a aircraft here if you want to say about this downwash, first we need to see what is the flow over an aircraft, how the flow will be flowing over an aircraft. That we already seen with the aerodynamics of aircraft, how it will looks like. So due to the aerodynamics of aircraft, the flow over the aircraft wing will be deflected, and due to that flow deflection only, like due to the flow deflection only, the pressure changes will happen. So due to that pressure changes, the flow aircraft will fly. Okay, but here when a wing, if you consider a wing cross section is like this, and here the flow is flowing over that one. So if flow is flowing over upward and downward, so when a flow is flowing over all over the wing, so when it comes to the wing tip, like this one, so wing tip is there. So there the higher pressure and lower pressure will be will cross over here. So because at the tip at the tip of the wing, so here the upper surface of the wing will have a lower pressure, and lower surface of the wing will have a higher pressure. Due to that only the aircraft is willing to motion. So when a flow is flowing over the aircraft, and here up to here to here, up to this fuselage to the wing tip, the flow will be flowing over that one. That will not be create any additional disturbances. But with the wing tip, here the flow from the upper low pressure and high pressure flows are getting mixing here. So that what will happen there, it will happen there, it will create a vortices behind that wing tip. So here due to that two pressure collisions, so here the vortices will be happen. So this type of vortices is called it as a wingtip vortices. So this wingtip vortices will be there, the velocity will be abruptly high. So due to that abrupt velocity only, that flow will have a different disturbances in its velocity also. So here due to this velocity, like due to this wingtip, so there will be an effect of downwash on the horizontal stabilizer. Like here, the due to this one, the flow is flowing over this one, no? And here the horizontal stabilizer will be there. So here the horizontal stabilizer, although flow will be continued here. So due to this wingtip vortices, here on the downside of the horizontal stabilizer, there will be a higher flow region, that is called vortex shedding. Due to that higher flow region, there will be a higher velocity on the upward and downward also. So that is called a downwash. Downwash means what? A flow will have a abrupt velocity under the aircraft and over the aircraft's airfoil surfaces. So with this downwash, like the effect of downwash produced by wing, such as horizontal tail, so that that downwash is caused by due to this wingtip vortices. These wingtip vortices will continue till this horizontal vortex, because these wingtip vortices will be continuous, and it will come up to the horizontal stabilizer also. Due to that, there will be a higher flow over the stabilizer also. That will give a new phenomena called downwash. So a wing produces a wing lift experiences. I mean the lift having on the wing will having a low pressure area on the upper surface of the wing and the high pressure area on the lower surface of wing. So that the higher pressure area and the lower pressure area will mix at the wingtip, so that the wingtip vortices will happen. So that only we have said now. So see here in the figure. So here the higher velocities will be there here, and here the lower velocities will be there. So due to this higher velocities, pressure will be low, and due to the lower velocity, pressure will be high. So here it will be high, it will be low, but here it will be both will cross over here. So due to the crossover, this wingtip vortices will be happen. So these wingtip vortices will continue up to this horizontal stabilizer also. So due to this one, the downward there will be a high flow will happen. So that flow is called as a downwash. So the wing, what is aircraft moves through the air and wingtips leave the circulation pattern behind the form of spiral. So that is called a wingtip vortices. And the wing vortex system into the induce a downward component of velocity, like a downward component velocity, like if you continue here now, so these velocities will gives a downward component of flow velocity, and that is called a downwash. So it is not in a because it is a symmetrical thing, so it will be both the side of the wing. So both the side of wing and both the side of airfoil. I mean horizontal stabilizers also. So from the Prandtl lifting line theory, like Prandtl have given the lifting line theory of an airfoil wing. So by based on that, the vortex is not restricted to the wingtips, but consists a whole vortex sheet behind the wing also. Like because of these wingtip vortices, the whatever the vortex sheet means what, the velocity flow over that wing. Like whenever a flow is flowing over that one, that will share, that will form a layer over that one, that will form like a sheet only. So due to the vortex sheet, so this won't be end up to end after this wing. This will continue up after this wing also. So like this, wingtip vortices also continue till this stabilizer. So this vortex sheet accounts a downwash at the wing and the tail. So downwash velocities are not constant across the span of the wing unless the lift distribution is elliptical. Like due to how that lift will be there, like lifting line theory when you see. So if it is a wing like this, so when a flow is flowing over this one, so when a flow is flowing over this one, so due to this flow, the flow will be like the lift will be generated like a elliptical type only. So this lifting line theory also we have discussed in, we come across in aerodynamics. So the constant, this downwash velocities at a given distance behind the wing will vary with respect to the distance from the fuselage. So the span-wise horizontal tail is small compared to the wingspan, because the tail part is a less span compared to the wingspan. So the downwash velocities experienced by the tail almost constant across the span. So the effect of downwash is to reduce the angle of attack of the tail. Like whenever the downwash is high under the under this tail, what will happen whenever if you're finding out to give some angle of attack to that one, so we need to give more force on that more force on the downward, because when the flow velocity is high at the downward, so that what will happen, the high upper pressure will be high and lower pressure will be low, but the reverse should be happening in reality, because upper pressure will be high, lower pressure, lower pressure will be high and upper pressure will be low, then only the lift will produce. But if it is in a reverse condition, due to this downwash, what will happen, we need to give additional force for getting the lift, so that the lift will be, because the upper force will be dominating compared to the lower force, so that the lift will be decreased. So these downwash components will gives you the decrease in lift also, right? So then you see the angle of attack changes with respect to the downwash. So how that the downwash angle of attack of horizontal stabilizer is look like. So if it is a wing chord line and it is a alpha reference line, and see here, so the velocity changes. The velocity changes is explained with epsilon e, and the component of downwash velocity is dw, and the alpha t is the tail angle of attack, and this is the actual velocity of the velocity over the tail. So there This I is called as incidence, angle of incidence already. That means the stabilizer will be having with a default angle of attack with flow, and the alpha, the alpha is the angle of attack with respect to the chord line, and and the dw is the downwash velocity at the time, and the epsilon is the downwash angle. So that epsilon is called it as a dw by u in radians. Like dw by u is the dw is already a velocity component only, and u also is in u also velocity component. So that will find the value in radians. So if there is w1 and w1 is the value at this is the value, this is the velocities in linear direction, and the downward direction, if it is w is the downward direction velocities, and the t1 t2 are the time time rate of change from one space to another space. So then the with respect to the time change, that is called delta t, from t2 time to t1 time, then you can change, you can get the values for w, like what. So we can say like delta alpha, like the necessary investigative effect of change in w with the vertical velocity and angle of attack of the tail can be defined with the delta alpha will be w by u. For w naught, w naught is at zero angle of attack. The initial velocity of w will be zero. Then the if w is still changing from one time to another time, like I said no previously, if a w changes from time t1 to t2, then what will be the w, the rate of change of w1 with respect to t. So that the rate of change of w1 will be w1 plus dw by with respect to dt and delta t. So the delta t is what we have already given, that is t2 minus t1. Then the equation the aircraft is moving at a finite velocity through the air mass, and with a finite time, the effect of change in velocity w will reach the time. So the time expressed by the relation this time rate of change, generally how we can say, like u will be meter per second means L by t. So if it is in L by t, then what will be t? T equal to L by u. So like with respect to t, that length will be lt, and u is the linear velocity. Then delta w is what? Like time rate of change on downward velocity of the aircraft. So the downward velocity of the aircraft we already given with the dw by dt into delta t. So the delta t we have expressed in terms of linear velocity with the lt. So the total delta w can be write it like dw by dt into L by ut. Okay, so here the lt is the distance between the quarter chord and the wing mag and wing main chord, and the quarter chord point of the horizontal stabilizer. Like if it is a wing, then quarter chord of the wing will be like what? So if it is a airfoil section, quarter chord will be up to here. So from here, the reference point taken from here, we will get the velocity, time rate of change, and that length of the chord also. So the length of the chord we have taken from the quarter chord point of the airfoil section. Okay. So then the amount of downwash, if you want to express the thing for amount of downwash, so depend upon the angle of attack of the wing, and thus the dependent of the vertical velocity of the wing. So therefore, it's said to be downwash at the tail is proportional to the vertical velocity of the wing. Like whenever due to the vertical velocity of the wing, we will be having, the vertical velocity of the wing will be given due to the wingtip vertices. So that wingtip, the vertical velocity is equal to, directly proportional to the w component w. Component w is the the downward velocity component. So if it is a proportionality, then if you want to take it out that proportionality constant, so with respect to a time t, that downwash we have given with dw, that will be equal to k into w. So if we say if we know the differentiation for this one, like delta dw will be equal to k into delta w. So the delta w we already given the relation previously. So that will be like what, k into lt by u into dw by dt. So that will be how the k into lt by u into w naught. So dw by dt we can write it like w naught. So then the delta dwt will be like what? So k k lt dash into alpha dot also. So the change in downwash at the tail to a change rate of change of angle of attack of the wing. So this result in a change of angle change in angle of attack of the tail, causing a small change in lift, small change in lift also. Thus the jet force in the pitching moment also will include. So because of the angle of attack change due to the downwash component, there will be a change in angle of attack also if we have given, so that jet force, like what will be the downward forces, that also will change. So if you want to make the values for that, so how it will be looks like suppose you can take the linear axis forces, like in a linear axis, what are the forces, like the drag of the horizontal stabilizer will be very small compared with the wing. So the drag of the rest of the aircraft will be generally 10% of the zero lift drag only. So the forces acting on the tail will be the drag forces acting on tail will be neglected compared to the wing forces. So the linear forces acting on the wing will be what? Fx will be equal to t minus d, like we already said now, the forces direction. So this will be w and this will be t, this will be l, and this is d and this is t. So this is in x direction and this is in z direction. So if it is if you are making it in linear direction, that is called fx. So what will be the resultant force change? That will be thrust minus d, because thrust force should be always greater than the drag force. Then only the aircraft will flow forward. So the t minus d. So the d is drag force. So for the drag, what is the equation? Half rho v square into s into cd. So that only we have written here. So then if you make the differentiation of df with respect to u, then what it will be? So dou t by dou u minus cd cd rho into u will be like with respect to u or u we are doing. So that will be like what? U into s minus it's like a uv formula only. This will be u and this will be v. So dou cd by dou u into rho u square by 2. So the dou f by dou x can be right like this. So then the cxu is the change in the force in x direction, like we have say here now. So suppose we can take a constant like a cxu in a linear direction with respect to x, the rate of change of forward velocity. So the force in x direction when the aircraft is in equilibrium flight with the w naught is 0, like actual velocity component at a zero condition is 0, then depends on the thrust and drag. The thrust vector may be not aligned with the velocity vector at the aircraft, but the angle between these two vectors normally very small, because the two force vectors will be always in a same line, but there will be some changes in drag and thrust also, like if it is a drag and if it is a thrust, so there will be some angle between that force vectors, but it is very small. So the using the small assumption in the cosine angle of cosine angle between these four vectors are replaced by 1, then what it will be? The CXU will be U by SQ into dou f x by dou u. This was we already expressed in last previous thing. So previously the CXU we have derived that stability coordinates like a big list we have given in the last video. If you refer my last video, then you can see that one. So CXU, CXZ, and CMA, CM alpha, CM Z also. We have given a list of derivatives, and if you find in any textbook also, prescribed textbooks that have already given in my reference textbook, there if you find, so you can find the stability derivatives description. So that stability derivative we have given with u by SQ into dou f x by dou u. So the dou f x by dou u with respect to u we already given. So what is the dou f x by dou u? So dou f x by dou u we have given in previous thing, like what? So that will be like dou t by dou u minus what is this one? Minus CD rho u square s minus dou CD by dou u into u. So that only we have directly given here. So that will be u by SQ into dou t by so if you multiply with this one, so you so what it will be? So that will be u by SQ into dou t by dou u minus CD rho u square s into u by SQ. So S and the Q is what we already given, half rho v square. So half rho v square if you substitute here, what it will be? That CD into rho Q square by half rho u square. So rho u square and this will be cancelled. So that here it will be 2 CD. So 2 CD will get. And another term is what? Another term is dou CD by dou u into rho u square s by 2. So dou CD by dou u into rho u square s by 2 into u by SQ. So u by SQ will be like how it will be? Rho u square rho u cube by 2 into half rho u square. So this rho gets cancelled and q. So that will be u into dou CD by dou u. So the final equation will be what? U by SQ into dou t by dou u minus 2 CD minus u into dou CD by dou u. Right? So that will be the expression for CXU. And then for a jet aircraft, the thrust is essentially constant. So thus the dou t by dou u is generally like thrust with respect to u is generally 0. So however, for a propeller driven aircraft, the thrust decreases as the velocity increases. So thus the d2 by du will be dou t by dou u will be negative. So the variation of drag velocity with respect to velocity is due to the Mach number effect only. So especially in transonic region, the CD varies with the Mach number at a constant angle of attack. So below 0.6, the dou CD by dou E is identically almost equal to 0 only. So you can see that the details from the appendix D in reference textbook one we have already given. So that so then we have given the constant stability derivative with respect to x we have given as a CXA. Now if it is in a z direction, like with respect to u, that CZU will be like what? With respect to u, if you want to with respect to z direction, if you want to find out, so what are the forces in z direction? So the forces in z direction will be like what? So Fz equal to W minus L. So the W will be high, so L will be low. L will be low only. So if Fz will be lift force is acting reverse direction, so that will be L. So that is what half rho u square SCL. So that is the expression for lift force. So then what is the dou Fz by dou u? Again, with respect to the linear velocity, what is the change in force with respect to that one? What it will be like with respect to u or u we are doing, no? So that will be like minus CL rho u s rho u s minus dou CL by dou u into half rho u square s, right? So this is the expression for dou f by uh, dou f z by dou u. Then what will be the again if you are multiplying that CZU, again we have given in last class, CXA is by like what u by SQ into dou f z by dou f x by dou u we have given, like that CZU also u by SQ into dou f z by dou u. So what it will be like u by SQ into dou f z by dou u will be what? So again it will be like what? So CL rho u s. So also the Q will be half rho u square. So if it is like a half rho u square, that u by SQ into CL CL rho u s. So CL rho u s SS will gets cancelled, and u by half rho u square into CL into rho u. So that will be u, and rho gets cancelled. So that will be like what? Uh, the 2 will be going up, so that will be 2 into CL. So that is the first term, and the second term will be like what? What is the second term? Dou CL by dou u into half rho u square, yes, into u by s into half rho u square. So half rho u square. So this will be rho u square, and half of that cancel. So that will be u into dou CL by dou u. So here the second term is this one, and the first term is this one. So then what will be the total expression for CZU will be what? So u by SQ into dou f z by dou u will be equal to minus 2 SCL minus u of dou CL by dou u. So if you can write like CZU equal to minus of 2CL plus u into dou CL by dou u, right? So this is the expression for that one. So the variation of lift coefficient with respect to velocity is primarily due to the Mach effect only. The lift coefficient is normally decreases very rapidly when tangent tangent equation, then rises again. So at Mach number 0.6, like the tangent region 0.6, dou CL by dou u, that means the rate of change of lift with respect to u will be identically 0. So that also we can get it from the appendix D. So then again it is directly, I mean, if dou CL by dou u is identical to 0, then that stability derivative is directly depend on the lift coefficient only. Okay. So so this is all about first part of the stability derivatives of longitudinal equations of motion. So other part is there with I mean, here we have derived that downwash components and linear components of stability derivatives we have defined, and afterwards the lateral I mean the angular moments and angular moments in linear and angular moments in the downward direction also we will find it in next class. So in the next class we will see the part 2 of this continuation only, like a longitudinal equation of motion with respect a longitudinal equation of motion derivatives with respect to that angular effect, I mean angular moments effect also we will see it in next class. Okay, so these are the reference books. So the reference 1 stands for Blake Lock GH, that is automatic control of aircraft and missiles. So you can refer that textbook for further information. Okay, thank you.
like, share and subscribe. Hit the bell icon for more updates.